this force X by the length Y. And we could show that this is the integral of the stress distribution from the bottom of the laminate, negative T on 2, to the top of the laminate, T on 2, of the stress distribution in X on dz. Right. So this was something that helped us to define the relationship between the forces on the laminate and the stresses that are developed in the laminate. Okay, so that was specifically for line load in the X or a force in the X, but we could also do something similar in the Y, not Fy, we want Ny is the integral from negative T on 2 to T on 2 of sigma Y dz, and similar, Ns is the integral from negative T on 2 to T on 2 of tau xy dz. All right, so kind of giving ourselves a shear force given the applied shear stresses that we have. All right, we could write that in shorthand. In sort of like matrix form. And that is Nx, Ny, Ns equal to the integral for all these guys from negative T on 2 to T on 2 of the various associated stresses. Here this will be sigma x, sigma y, tau xy, all integrated over the thickness of the laminate dz. Right? So this is writing the force as a function of the stress. So we can have similar relationship between the moments and the stress. And that is the moment in X, moment Y, and the moment in shear, which is kind of like the torque on our laminate, is the integral negative T on 2 to T on 2. And here we've got an extra Z kind of floating around just because of a moment arm that we need to properly relate the stresses and the moments. So here we have a variable which is the location and thickness of the laminate Z multiplied by the appropriate stresses X, sigma Y, and tau X, Y, integrated dz. Right? So here we're relating forces Nx and Y and S to stresses, sigma X, sigma Y, tau X, Y, and also we're relating moments per unit length, Mx, My, and Ms, to stresses which we apply sigma X, sigma Y, and tau X, Y. Right? So we weren't really done. We could recall our relationship between stress and strain. And that is, if we write it in shorthand without its full-blown 3x3 glory, we could write that the stress in layer K, XY direction equals the stiffness of that particular laminate, that particular layer, the particular laminar K, XY, multiplied by the mid-plane strains of the laminate that developed in our global coordinate system XY, plus the distance to lamina K, which we call Z, times Q bar XY of laminate K multiplied by the curvatures that we developed in that particular global coordinate system, kappa XY. All right, so we've got a lot of stuff on the white pad here now. We got vector notations, we've got matrices, we've got integrals. It's all probably seeming a little abstract right now, okay? So hopefully in the next lecture or two, we can sort of bring it down to concrete reality with a couple of examples looking at maybe like what some of these things actually look like for a laminate that we might create with certain forces and stresses that we might apply. Okay, so it all looks a little cumbersome right now, but I promise that we'll kind of come back down to reality in the next couple of lectures. Okay, so that's about where we left off last time. All right, so going forward, we kind of have the new stuff. All right, so now new stuff. All right. Let's see, is Matt here today? I don't know if Matt's here or not. Well, anyway, I got a joke because he wanted some joke. Pickup lines for COVID-19. Okay, maybe a little too soon, but whatever. I'm falling into madness here anyway, so whatever. I got to entertain myself somehow. You can't spell quarantine without URAQT. Okay. Terrible. I got more, don't worry. All right, so let's talk about new stuff. So here we know the general relationship between stresses and strains and curvatures that develop. And up here in this expression that relates forces to stresses, we know stresses. Okay? So what we're going to do is plug this guy here into these two different equations. All right? This will provide us a very sort of long form relationship between what is the forces and moments we might apply and the strains and curvatures on the laminate. All right? So new stuff here. And if we call this star, we're going to plug star into the vector n and the vector m. All right. So this will give us some additional relationships which might be helpful. All right. So remember last time also we discretized some of those integrals to sort of help ourselves and talk about the stress distributions in each one of the individual layers. And so ultimately, if we plug these guys into each other, so plug star into these relationships for the forces, we could come up with something like the vector that is n in the xy coordinate system. Here, remember this is 3 by 1 equal to, and I'm just going to kind of write this here, the summation from k equals 1 to n. So we're summing over all of the individual lamina layers in the laminate. This is q bar k multiplied by z k minus z k minus 1. Let me just get this down here, and then we'll sort of explain the terms. Here, this is the midplane strain component, plus here we have a 1/2 that hangs out. Summation from k equals 1 to n of our stiffness of layer k multiplied by zk squared minus zk minus 1 squared. This all times, sorry, I didn't quite fit it in here. Yeah, I can make this bigger. Just for now. Multiplied by the curvatures kappa in the xy coordinate system. Okay, what have we done here? All right, well, we've moved from this general expression and this general expression, which are integral equations, and plugged in this guy there. Okay. I've also taken the time here to actually perform the integration as well. Since each one of the individual, since the expression here on the right-hand side, they're all sort of functions of the individual lamina, we can actually integrate within the individual lamina. So I've sort of done that and actually performed the integration here to ultimately end up with a relationship between the forces that we apply, this n vector, and the relating strains and curvatures that can appear. We have a similar expression for the moment. So the moments applied relate to the strains through a similar expression after plugging in the equation that we know about the stresses. So this 1/2 comes from the integration. It's a constant that gets pulled out of that after the integration. K equals 1 to n, where n is the number of lamina. Q bar k times zk squared minus zk minus 1 squared multiplied by the midplane strains xy plus, here now we have a 1/3 coming out of our integration. Summation from k equals 1 to n of our stiffness matrix q bar layer k multiplied by zk cubed minus zk minus 1 cubed times the curvatures that develop kappa xy. Okay, now this is cumbersome and sort of complicated. All right, I'm just going to proceed forward, push forward a little bit, and then we're going to talk about what each one of these little pieces are. Okay, so I need to bring back my pad here. I wonder if there's a way that I can like zoom out. I'm not quite exactly sure. I guess for those of you still writing, I'll start to keep this up. All right, so this is sort of long and cumbersome as it is currently written. So usually it is written in a shorter hand. And usually in shorthand, it's written as the forces that you apply in the global coordinate system xy equal to some matrix A that encompasses more or less all of this stuff here, multiplied by the midplane curvatures, plus some matrix B that encompasses what would be all of this stuff here, times the curvatures that develop, kappa x, y. All right, so this is sort of a shorthand notation to describe what we've sort of written above. We can do a similar thing for the moments. Here, the moments that are applied, xy, equals all this stuff here, which is the same as all of this stuff here. So that is the B matrix, okay? Since this here is a matrix quantity, times the midplane strains, plus here all this stuff, which we'll label as D, times kappa xy. All right, so these generally are the relationships between the forces and the moments that we apply and the strains and curvatures that develop on the particular laminate. Right. Complicated, I know. So here, let's be very explicit then about these matrices A, B, and D. So we sort of shorthand wrote them, but let's actually lay them out explicitly. Where the matrix A here is all that stuff in that first equation, which is the summation from K equals 1 to N of the stiffness matrix of layer Q, of layer K, multiplied by ZK minus ZK minus 1. And remember, this is the bottom of lamina K. This is the top, sorry, I said that wrong. This is the top of lamina K, and this is the bottom of lamina K. Okay, so this is just dimensions that we have from putting our coordinate system on a particular piece. All right, so this is the A matrix. We also have this B matrix. Summation from K is 1 to N of the stiffness matrix of layer K times zk squared minus zk minus 1 squared. And I forgot a half term out here. Sorry about that. And then finally, the D matrix is 1/3 summation from k equals 1 to n of the stiffness matrix Q bar of layer K multiplied by zk cubed minus zk minus 1 cubed, right? So these generally are your stiffness matrices for the laminate, right? I don't like that box very much. I like nice hard corners, I guess. All right. So we've gotten a lot down on the whiteboard here and probably seems a little bit abstract. Let's just kind of writing up some of these things in shorthand, and then we'll actually describe what the physical interpretation of some of these particular matrices actually are. I think kind of just writing all this math and doing all this sort of stuff, we kind of lose the actual physical interpretation of what these things are. So let's kind of finish writing the shorthand notation here that relates the forces to the strains that develop, and then we'll sort of talk about the physical interpretation of what each one of these particular matrices mean. Okay, so with that said, we can write the most, here have the most so the most general form relating forces and moments to strains is to actually stack up in a 6 by 1 vector, and x and y and s, mx, my, and ms equal to a big old 6 by 6 matrix containing what would be all entries of the A matrix up here. So this is a 3 by 3A. All entries of the B matrix, all entries of the B matrix, and all entries of the D matrix, multiplied by the strains that develop. This here is epsilon x 0, epsilon y 0, gamma xy, midplane. Here this is kappa x, this is kappa y, this is kappa x y. Okay, so this is a full relationship between the forces that we apply and the strains that develop. Okay, so here forces and moments applied. This here are strains that develop. And this here is the laminate stiffness matrix. Okay, this laminate stiffness matrix here is a 6 by 6, where each one of the 4 quadrants that we have in that particular matrix is a 3 by 3. Right? So more often seen as simply the following: N M equal to A B B D times epsilon 0 and kappa. Okay, how are we doing? You scared yet? Recording didn't start. Ah, crap. I forgot about that. Oh, well. Right. Thank you for reminding me. Oh, the recording did start. Oh, someone started it. Okay. Thank you, Anson. Apologies, I forgot. Thank you for catching it. Okay, so we more often seen it in this particular notation here, where we have sort of the forces and moments sort of on this side. We have the strains and curvatures that are formed on this side. And then here is our laminate stiffness matrix, ABBD. All right, so just went through a lot of math there. Let's actually bring it back down to reality. Let's talk about a physical interpretation of the A matrix, the B matrix, and the D matrix. So what do these things actually represent physically? Okay, well, if we look at this expression up here, we can sort of just generally think about the relationships between the forces we might apply and the strains that developed by thinking about the traditional matrix mathematics associated with this particular arrangement, okay? So let's be very clear here and to say things like A, B, and D, which we defined up here, are going to be functions of geometry. So that's like the thickness of the individual layers. They're going to be function of material properties. That's sort of this portion here, which is the stiffnesses of each of the individual layers inside of the laminate. And then it's also a function of the stacking sequence and plies. Okay, so as we're looking at summing over all of the layers inside of the laminate, we're going to have different variations for different stacking sequences. Okay, so whether we have a 0, 0, 90, 90 or a 0, 90, 0, 90, things are going to change. Okay. Okay. So A, B, and D are functions of geometry. It's like the thickness of the individual layers. It's functions of material properties. So the stiffnesses of the individual layers, for instance, and stacking sequences. Right? You may think of these particular stiffnesses, A, B, and D, as kind of like the average stiffnesses of the various layers contributing to a global stiffness of the particular material. Okay, so I've written this in the notes, but let me sort of explain what I mean when I say that they are the average elastic parameters of the multidirectional laminate. Okay, and let's sort of interpret what these actually sort of represent. So what I mean by that is, you know, maybe layer 1 contributes heavily to the stiffness in this direction, but layer 2 doesn't particularly contribute heavily to the stiffness in this direction. And A is trying to capture the idea that one is stiff, one is not stiff, and we have sort of this like average that's working between the two of them. Okay? So it's an attempt to sort of capture the relative stiffnesses of each one of the individual layers and sort of sum them all together and somehow sort of average them. Okay, so first let's talk about the A matrix. All right, The A matrix is the matrix that sort of relates in-plane loading to in-plane strains. To in-plane strains. Okay, so let's look at, sorry, I'll leave that here for just a second while people maybe are copying that down. It's the matrix that relates in-plane loads to in-plane strains. So this is the stiffness that you're probably most familiar with, right? Like the elastic modulus in one particular direction, okay? If I, pull a laminate in this particular direction, it's going to strain in that particular direction. So the A matrix is the relationship between the actual loads that we apply and the strains that are developed because of those particular loads, the longitudinal strains that are developed. And we can sort of see that with the matrix math here. So N here on the matrix math for this particular piece is going to be a combination of A times epsilon 0, right? So we're kind of doing our traditional matrix math where we go across the rows and down the columns, okay? N is A times epsilon 0 plus B times kappa, right? So N is A epsilon 0 plus B kappa, all right? So A is the stiffness that relates the applied loads here, the longitudinal loads N, to the longitudinal strains that are developed, all right? That sort of makes sense. Right? B is a little bit more difficult to wrap your mind around, but is something I think we can talk through. So B is the coupling stiffness matrix. Okay, which relates either in-plane loads to curvatures or applied moments to longitudinal strains. Okay, so what do I mean by that? All right, well, the B matrix tells me if I apply a load longitudinally this way, how much will that laminate curve because of that applied load? It's this coupling matrix. It's a lot sort of like that shear coupling coefficient that we've talked about before for individual lamina. Remember the shear coupling coefficient, if we applied some strain this way, the shear coupling coefficient told us how much it was going to shear when we did that. It's a strange property of composites that comes up because, pulling on the composite this way might induce some shearing, right? The same idea here now with laminates is if we pull on the laminate, not only is it going to strain longitudinally, but it might also curve out of the plane or curve the other direction or possibly curve with some like torquing sort of curvature as we apply these in-plane loads just based on the general material inhomogeneity or orthotropic behavior. All right, so it's a little bit difficult to wrap your mind around that. So one idea is relating in-plane loads to curvatures. So let's talk about that. Again, remember back up in this equation here, we have N is A times epsilon 0 plus B times kappa. All right, so the matrix B relates applied loads to curvatures which may develop. right? So again, this idea of I can pull on this and the laminate might actually curve in response, right? So that one's a little bit difficult to sort of understand. And that is one place we see the B matrix relating in-plane loads to curvatures. Another place that we see it is relating applied moments to longitudinal strains. So that comes in the second equation here when we're talking about the equation for M. And we know that the equation for M is going to be B times this B times epsilon 0 plus D times kappa, right? So that's just this traditional matrix mathematics relating those particular pieces. All right. So the B matrix can also relate applied moments to longitudinal strains that develop. Again, this is kind of the same idea. If I apply a bending moment to my laminate, all right, let's see if I can find that. Right. So if I apply a bending moment to my laminate, I can't actually do it because this guy's actually really stiff. But if I apply a bending moment to my laminate, this B matrix tells me that when I apply that moment, my laminate might actually get longer or shorter when I apply that moment. So that's like elongating or compressing because of a moment that has been applied. Okay. Lastly, the D matrix. This is the flexural stiffness matrix. Which relates the applied moments to curvatures, right? And just like we had the A matrix that related in-plane loads to longitudinal strains, just sort of an intuitive idea to us mostly. We also have the D matrix, which relates the applied bending moment to how much the laminate curves. All right, again, this sort of like intuitive idea that if we apply a bending moment, the laminate's going to curve. All right, so I think the A matrix and the D matrix are pretty easy to understand in the way that they relate. For the A matrix, longitudinal loads to longitudinal strains. And the D matrix relates applied moments to curvatures of the laminate, which, you know, those are sorts of things that we would expect to occur under normal conditions. However, there's also this other guy, this B matrix that hangs out that tells me, okay, if the B matrix is non-zero, then if I apply some loads to this structure, then it's going to curve. Or if I apply bending moments to this structure, it's going to either get longer or get shorter. Yeah. So some physical interpretations there of what we actually mean when we're talking about these A, B, and D matrices. Okay, how are we doing out there? We got any questions? I'll check my questions here. All right, it looks like we're okay. No questions. Okay, let us continue. All right, so I wanted to at least make my way through a little bit of an example. So I'm going to pull up the slides here really quick and sort of at least lay out the beginnings of an example where we're sort of bringing what looks like very abstract math here with integrations and summations and matrix math and all that sort of stuff, bring it down to reality to talk about what some of these matrices might look like given real laminates that we might think about creating. All right, so I'm going to share here, not my white pad, but I'm going to share my PowerPoint slides here for just a second so that we can sort of motivate an example and talk through this example here. All right, so let's consider a symmetric laminate like we have here. This is a 0, 45, 45, 0 laminate. Okay. Okay, and I've noted this as a symmetric laminate because the stacking sequence is symmetric about the midplane. So if we say that the midplane here occurs between the 245 layers, then we have symmetry with 45 above, 45 below, and zeros, 2 above and 2 below. Okay, so with this particular laminate, we lay out some general geometry. All right, so I'm going to actually see if I can sort of copy this image here and bring it over to my whiteboard so I can actually make some notes. As large as it goes. There we go. Okay, so let's go over to the white pad and I'll sort of make some notes on the white pad over here and we'll work through this general example. All right. I think it'll be easier to work this guy in the white pad. Okay, so here's our example with a 0, 45, 45, 0 laminate. And we're defining like the location of the bottom and the top of each particular layer using the variables here, Z. Okay, so for instance, like if this is layer number 1, this is layer number 2, this is layer number 3, and this is layer number 4. So this would be K equals 1 through 4. Okay, so we use K to denote which layer we're particularly in. Then we have here this Z0 is the bottom of layer 1, right? Z1 is the bottom of layer 2 and the top of layer 1 and so on and so forth. Okay, so we can define these directly if we say that the total laminate has a height of h. Okay, so we're here using h now instead of t. And we'll say things like, all right, Z0 is that location negative h on 2. Z1 is that location negative h on 4. Z2 is that location 0. We have Z3 is that location h on 4. And Z4 is that location h on 2. All right, so we're able to define the locations of each of the lamina tops and bottoms in the laminate stack. All right, so what we're going to do then is let's solve first for generally the A matrix, or what the A matrix might look like. All right, so we'll walk through this slowly so you sort of get a concrete idea of what this A matrix actually is. All right, so the general equation for A like we laid out before was that the matrix A is the summation for K equals 1 to N. For here, it's going to be 4 layers, so we're going to have N equal to 4, of our Q bar K multiplied by ZK minus ZK minus 1. All right, this is our general equation. All right, so A is a 3 by 3 matrix. So this is actually 9 equations, okay? For A11, A12, A13, A21, A22, so on and so forth, okay? So we'll just keep it general by saying that we're going to calculate the IJ entry of A, right? And let's motivate the IJ entry of A by just calculating for now, like the 1-1 entry of A. So let's calculate A 1-1, the 1-1 entry of our 3 by 3 matrix A. So if we do that, we're going to sort of blow up this summation and actually look at each of the individual pieces. So here A11 is the summation from K equals 1 to N. So we're going to have 4 pieces of this summation for the 4 different layers that we have. Okay. So let's look at what this guy would be for layer number 1. All right. So for layer number 1, Q bar K is the entry, which is Q11 for Q with theta equals 0 degrees. Okay. So since layer number 1 is oriented at 0 degrees, then we want the 1, 1 entry of Q for theta equals 0 degrees, right? This is then going to be multiplied by ZK, which we know is Z1 minus ZK minus 1, which we know is Z0, okay? And then this is plus, so this is sort of like the contribution of layer number 1 is the stiffness in the 1, 1 of layer 1 multiplied by the thickness of that particular layer, Z1 minus Z0, right? Plus, here we have the next contribution of the next layer. This is Q bar 1, 1, evaluated for theta equals 45 degrees, okay? Because this is the orientation of the second particular layer. And this will be multiplied by Z2 minus Z1. Okay. We'll continue with the contribution of the third layer, which is Q bar 1, 1, evaluated for theta equals 45 degrees, multiplied by Z3 minus Z2, plus the contribution of the fourth layer, which is the 1, 1 entry of Q bar evaluated at theta equals 0, multiplied by Z4 minus Z3. Okay, and this is the whole expression simply for A11, right? So we've laid out explicitly things like Z1, Z0, Z2, so on and so forth. So let's kind of make some simplifications here for those entries. We'll have Q bar 1, 1 times theta equals 0 degrees for Z1 minus Z0. Okay, so this is going to be Z1 minus Z0. Let's just put them in here directly. Z1 is negative H on 4 minus a negative H on 2, which is Z0. Or if we wanted to simplify this, this simplifies to H on 4. All right. So let's actually just go ahead and write it as H on 4. Okay. Plus Q bar 1, 1 evaluated for theta equals 45 degrees. Again, Z2 minus Z1 is just the thickness of the 45-degree layer, which again is H on 4. Plus Q bar 1, 1. This is the contribution of the third layer. Evaluated for theta is, again, 45 degrees by H on 4. Plus Q bar 1, 1 for theta equals 0 degrees multiplied by H on 4. All right, so now you see that each one of the individual stiffnesses of each one of the individual layers, okay? So here we have contribution from layer 1, here we have contribution from layer 2, layer 3, layer 4. Each one of them is contributing a certain amount of stiffness when we actually pull on the laminate, how much it's actually resisting that pulling to give us a certain amount of strain. And each one of those is sort of normalized, or the contribution of each one of these is sort of magnified by the value H on 4, right? So each one of them has a weight of H on 4. In this particular example, all the layers are contributing equally to the stiffness, let's say, of this particular material. As we pull on it, its resistance to straining in that particular direction, because we know the A matrix is the relationship between the applied loads that we have and the strain that develops in that particular direction. Okay. So we'll also notice here that we have some redundancies. So Q bar 1, 1 for theta equals 0 degrees appears twice, and also Q bar 1, 1 for theta 45 degrees also appears twice. So what we're going to do is we're going to simplify this and sort of combine terms. And you're going to be left generally with A11 equals H on 2, okay, because I'm going to pull H on 4 out from each one of these. And notice that we have 2 of each contributing stiffness, multiplied by Q bar 1, 1 for theta equals 0 degrees, plus Q bar 1, 1 for theta equals 45 degrees. Okay, and this is the 1, 1 entry of the stiffness matrix A. Okay, H/2, that's pretty easy to understand. It's half the thickness of the laminate. And these guys, Q bar 1, 1, Q bar 1, 1 for theta is 45 and for theta is 0. These are the stiffness matrices of the individual lamina rotated appropriately to get to where they need to be. So you did this on homework number 1, where I gave you or you calculated what the Q matrix would be of a particular lamina, and then you rotated it 45 degrees to get into another orientation. Okay, so Q bar 1, 1 might have the general appearance of like information here, 0, information here, 0, 0, 0, information. This is generally what the Q matrix looks like when it's in principal coordinates, meaning that it's oriented at theta equals 0. And then when you transform this using the transformation matrices, you're going to get to Q bar for theta equals 45, which will have some other matrix that will have filled entries, but will still be symmetric. Okay, so you know how to calculate all of the things in this particular expression. Okay, all right. So we calculated here for A11, but this is general for all Aij. We didn't do anything specific related to the 1, 1, 1, 2, 1, 3 entry, so on and so forth. So we can generally say that all entries of Aij, is H/2 multiplied by Q bar Ij, theta equals 0 degrees, plus Q bar Ij for theta evaluated at 45 degrees. Okay, and this is the calculation of entries of the A matrix. All right. So that's that. We'll pick this up on Monday and do the rest of this, calculating the B matrix and the D matrix for this particular laminate. All right, that'll be it for today. Thank you for starting the recording since I forgot. I'll stick around if people have a couple questions. Otherwise, thank you for coming and have a good weekend. End of week number 1. Rawr. Yeah, I know. I got more of them too. You can't spell virus without you and I.